Hello everybody. What I want to do today, hopefully it won't take too long, is I want to prove an equation to you. So let me fire up my pen here. What color am I using? Let's use a blue. Let's make sure it's going. Here's the equation. And if you would have reviewed your textbook over the weekend or maybe last night in sections, I think it's chapter 4.5 to 4.6, you would have seen this equation. And this equation gives you the acceleration for a particle that's moving around a circle at a constant speed, and the circle has a certain radius. And what I'd like to do is prove this equation. So let's begin. Let's start with, let's draw a circle right here. And let's put in an axis. And here's a particle. These dots are the particle, and it's traveling around the circle this way. At some instant in time, it's going this way, and I'll call this V initial. And at some time later, it's doing this. Again, if it's traveling in a circle, its velocity is always tangential to the circle. And I can define an angle theta here and a theta angle here. So basically what I'm looking at, I'm looking here with the particle initially a certain angle below the x-axis, and then up here it's that same angle above the x-axis in some future time. Because what I want to do is I want to apply the basic definition of acceleration to this particle traveling around in a circle. And this is the basic definition, that acceleration is defined as change in velocity over change in time. I can simplify that and look in each direction. Notice this is x and y motion. It's in a circle. A circle is a two-dimensional figure, so this thing has at different times x velocities and y velocities. So I can write this. That can be x over time, so the acceleration in the x direction is a change in the velocity in the x direction divided by time. And then in a similar fashion for y. There we have it. So what I'd like to do is I want to start to evaluate these. What it means, I have to break my velocity vectors, these guys, into the x and y components. Let's look at V initial first. Let's just draw a section of this circle that includes V initial. Here's V initial. Notice I can kind of draw a little coordinate system on here where this is x and y, where this coordinate system is parallel to this one here, parallel and perpendicular. Now, if here's my center of my circle and I'm kind of down here, notice I have this angle right here. I'm just going to write it over the y. There's this angle. Well, that has to be the same as this angle here, which is the angle that the velocity vector makes with this y-axis in here. Let me just draw it again so you can see it better. Here it is. Here's an axis drawn at the end of this velocity vector. And this theta is the same as that. What that allows me to do is I can say then, and we did this with projectile motion, that V I x is equal to VI magnitude sine of that angle. It's this component over here. And make that a little clearer. And VIY is equal to the magnitude of the velocity vector cos of that angle. And those are the two components. And again, this one is right here. And this one is that component there. The tricky thing at this stage, I believe, for you is to convince yourself that this angle is indeed that angle right there. And a little bit of geometry will get you there. Now, what about V final? Notice he looks this way. Because remember, the particle is right here initially, so it's headed tangential to the circle, so it's kind of up towards the x-axis, and then sometime later the particle has changed direction, and V final now is pointed this way. Now, again, if we here's our particle. If this is the center of my circle, and again here's theta. What I want to ask is where's this angle over here? It's actually right here. So this angle is the same as that angle. Again, I'll leave you folks to spend a bit of time verifying that. Notice what I can write. V final x is going to equal negative V final. And it's this component here, so it's opposite, so it's going to be sine of that angle. And V final y is going to equal, it's going to be a positive, it's this component here, V final magnitude cos of theta. Does everyone see where this negative sign comes from? It's because if you come over here, notice that this is a vector pointed in the negative x direction. You can see it up here too. You can see it's negative. It's pointed back. It has a positive y component. This part right here is pointed up, but this guy here is pointing in the negative x direction. So now we have these equations right here, and we can put them in here. So let me go to another page. Let me write these down again. V initial x is going to equal V initial, and it's sine theta, and V initial y is equal to V I magnitude cos of theta. And just see, did I do that right? They look like they're okay. And then we do the other ones. V final x is equal to minus V final sine theta, and V final y equals V final magnitude cos theta. Now again, let's look at acceleration in x is delta y, change in the velocity in the y direction over change in time. Acceleration in x is equal to change in velocity in x or change in time. Let's that's y, pardon me. These guys are x. Let's look at y for just a second. let's AY, acceleration in the y direction, has to equal velocity y final minus velocity y initial over delta t. And look at what that gives us. This, although I wrote my subscripts different, that's this one, and then this guy. So we can write this, v final cos theta minus v initial cos theta over delta t. And remind you again, this is just this. I wrote there I wrote it as v final y, and over here I wrote it as vy final. They're the same thing. Now look at this, and one thing to keep in mind, if this object is traveling around the circle at a constant rate, and that's the motion we want to look at in this instant, is motion where it gets around the circle in the same amount of time every time. That means their speeds have to be the same, which means that the magnitude of the velocities. So look what that acceleration in y gives you. It's basically a v, because let's just define this as just a large v cos theta minus v cos theta over delta t. And that is simply 0 over delta t, or 0. That means the acceleration in y, and I should say that it's average because it's over this time period. It averages to 0. So I just kind of use this thing here. This particle going from here to here has had 0 average acceleration in the y direction. And you can actually see that it actually has the same velocity component in y at this stage as it did here. Now, I think what I'm going to do is, if these videos get too long, YouTube doesn't like me putting them on there. So I'm going to break this up into 2 parts. So I'm going to stop the video now, having solved for the acceleration, the average acceleration in AY, and I'm going to, in the next set of slides, evaluate that one there. So stay tuned.